The goal of this video is to compute the definite integral of cosine of x raised to the 100th power from x equals 0 to x equals pi. We'll be able to do this, and it's a definite integral, which means at the end, our final answer will just be a number. In order to do this, what we're going to do is integrate some other powers of cosine, kind of spot a pattern, then we will come up with a general expression that will allow us to compute this result. Okay, so I want to compute the integral from 0 to pi of lower powers of cosine. Let's start with power 0. So I'm going to write cosine of x to the 0th power dx. And I decided today that I'm putting powers to the right instead of writing cosine 0x, which is just a notation. Anyway, cosine of x raised to the 0th power is 1. The integral of 1 dx from 0 to pi is pi minus 0. So my first example of a power of cosine integrated from 0 to pi is just pi. Okay, let's go up to the next power of interest, and that's actually going to be cosine squared. So what we're going to do is come up with a pattern for even powers of cosine. But we won't do 0, 2, 4, 6, all the way to 96, 98, 100. We'll come up with a pattern. So let's do cosine squared, and then we'll do to the 4th power. And I think that will be enough to figure out what must be going on. Okay, often if you see this kind of expression, your inclination may be to use power reducing, which in ordinary circumstances is totally fine. But the technique of interest for our final question that we're trying to answer is actually going to be integration by parts. You can come up with the antiderivative of the cosine function squared, or also the sine function squared, with integration by parts. And what you do is you recognize this integrand as the product of cosine with itself. That gives you the integration by parts decomposition. So that instead of thinking of this integrand as cosine squared dx, I'm going to think of it as cosine of x times cosine of x dx. Okay, with this u dv, we have du is negative sine of x dx, and v is sine of x. All right, that allows us to set up our right-hand side. It's going to be this product, so cosine of x, sine of x. We will plug in top and bottom bounds, and then subtract from that the integral from 0 to pi of this product. That's going to be negative sine squared. I have minus negative, so let's make that plus. And for the first and only time this video, I'm going to write sine squared rather. Okay, I made a choice today to put powers here. This is the only time I'm going to write sine squared, because in the future, every time I see sine squared, I want to replace it with 1 minus cosine squared using the Pythagorean identity. So as we work through a few more examples of this computation, whenever we realize that we have sine squared, we won't write it. We will write 1 minus cosine squared. So that's one observation to make. And the other is that the sine function is 0 at pi and 0. So if I plug in top and bottom bounds and I have a sine here in my product, this whole thing will vanish. Which means, as we do a few more examples of these, whenever we recognize this expression has sine, we might not even bother to write it. Okay, so let's go a little further. I think I will write one more time over here before we go down. This is 0. This is going to be the definite integral from 0 to pi of 1 minus cosine squared. That's just the only change I want to make at this moment. Okay. So our example computation that we're doing is now the definite integral of the cosine function squared from 0 to pi equals the definite integral from 0 to pi of 1 minus cosine squared. So let me rewrite this down here. And as I do so, I'm going to break this up into two integrals. The integral from 0 to pi of 1 dx. I'm really tempted to replace 1 with cosine of x to the 0th power, but I think that's a bit of overkill. So let me just write 1 dx, but you can make a note to the side that that would be the same as cosine to the 0, and then minus the definite integral from 0 to pi of cosine of x squared dx. Sometimes when students see this, they think we've done something useless because we don't know how to solve this. That's what we started with. However, we haven't really gone back in a circle. We haven't gone in a circle. We're not back where we started because I can actually bring this term over to the left-hand side, combine like terms, and then isolate that like it's a variable in an algebraic equation. So let me just do that right here. Going to add this over. And when I do so, my left-hand side will become twice the definite integral from 0 to pi of the cosine function squared equals the integral from 0 to pi of 1 dx, which we know to be pi. So we can go ahead and solve for the integral that we're interested in by dividing both sides by 2. Okay, this is pi, so I divide by 2, and I'm going to write it as 1/2 pi. And that's, of course, what you would get if you did power reducing instead, but this illustrates the general procedure. I would like to turn you loose on the next computation. I'll give you a head start, though. The next power that we're interested in is the 4th power. So I would like for you to start trying to do the definite integral from 0 to pi of cosine of x raised to the 4th power. It's going to be integration by parts, and let me give you the breakdown. Treat cosine raised to the 4th power as cosine cubed times cosine x dx. So set up the integration by parts where u is cosine cubed and dv is cosine of x dx. So it's the same expression that we have here. And then set up the right-hand side and try to take it as far as you can. You might be able to get all the way to the end, but I will come back and show you how to repeat this procedure, replacing the 2nd power with the 4th power. All right, let's see how you did. As I suggested, hopefully you set up u to be cosine cubed, dv to be cosine x dx, making du 3 cosine x squared times negative sine of x dx. So watch your chain rule there. And then v, just like before, is sine of x, which means when I start to set up the formula on the right-hand side with integration by parts, my first expression would be cosine cubed times sine. But again, we'd be plugging in 0 and pi. The sine would cause all of that to vanish. So I'm just going to write 0 there, and then in the future I might not even write that. And then we would have minus negative 3 times cosine squared sine squared. So I'm going to write plus 3 minus negative. The definite integral from 0 to pi, cosine squared. And then as promised, I'm not going to write sine squared. I'm going to write 1 minus cosine squared. And I'm going to use my exponent convention of the day. Okay, let's now, I'm going to write this like very shorthand here. I'm going to break this into 2 integrals, just like we did before, where the first one is 3 times the definite integral from 0 to pi. I'm just going to write c squared so that we can fit it on the screen. And then the second one is minus 3 c to the 4th, or cosine to the 4th. Okay. We just figured out what this was. This was pi over 2. This is what we're solving for. Just like before, let's combine it into an algebraic expression. So we will have 3 copies of the integral we're looking for come over, giving us 4 total. So let's write 4 times the integral from 0 to pi of cosine to the 4th. Sorry, that's supposed to be a 4th power, equals 3 times an expression that we already have on the board, which is 1/2 pi. Okay. We can now isolate the integral from 0 to pi of cosine raised to the 4th power by just dividing both sides by 4. And as we do so, we might recognize a pattern coming out. So we had 1/2 times the previous integral. So this times a half gave us the integral of cosine squared. And now we have 3/4 times what we had before. So pause for a moment and see if you can just conjecture what this number would be for the definite integral from 0 to pi of cosine of x to the 6th power. I'm not asking you to do this again. I'm asking for you to try to recognize a pattern. So based on what we have, pi, 1/2 times pi, 3/4 times 1/2 times pi, write down, again, a conjecture for what the next expression would look like. All right, I hope what you wrote down was, let's see, 1, 2, 3, 4, 5, 6 times the previous expression. And if you did, you're right. So this is now the integral of cosine of x to the 6th power, which means we can actually just go ahead and answer our final question, and then I will actually prove for you that the formula holds. So what is the definite integral from 0 to pi of cosine of x to the 100th power? If you need help coming up with the first term, notice here that the 6 is in the denominator, the 4 is in the denominator. So it would be 99 over 100 times 97 over 98 times 95 over 96. And you would take the product of all such fractions until you got down to these. Let me write times 3/4 times 1/2 times pi. Okay, so that is how you can build up a pattern to get all the way to cosine of x raised to the 100th power, integrating that function from 0 to pi. If you would like to see this formula justified, let me now set it up and I will show you that any such even power of cosine in the integrand can be written as a fractional quantity times the integral of the 2 lower power. Okay, it'll be clearer when I write it down. So let me step aside, erase this, and then I will prove the general relationship. Let's provide justification for the pattern that we just used by verifying it in general for any integrand of the form cosine of x raised to the 2n power, where here n is greater than or equal to 1. So the expression that we write down will start for cosine squared and then higher even powers of cosine. We will be building off of cosine to the 0th power. In other words, the integral from 0 to pi of 1 dx is pi. So that's like our base case. Just like before, let's do integration by parts, and I'm going to use that C and S shorthand. So U will be all but one copy of cosine. So cosine to the 2n minus 1. So that du will be negative 2n minus 1 cosine to the 2n minus 2 sine dx. Yes, that looks right. Then dv will always just be one copy of cosine here, so cosine dx, so that v is sine. Just like we've seen now a few times, the product of u and v contains a sine function, and when we plug in pi and 0, that will cause that product to just be 0. So I'll write kind of a placeholder 0 there to represent how u and v, what they evaluate to at the top and bottom bounds. And then we'll have minus negative 2n minus 1, so I will write plus 2n minus 1 times the integral from 0 to pi. We have cosine to the 2n minus 2 times sine squared, just like before. Let me break that up. And I think I will not use shorthand, debating it with myself, but let's do cosine to the 2n minus 2. And then instead of the sine squared, I'm going to write 1 minus cosine squared with my new convention dx. we really see everything that we've looked at so far. So this will break up. These two, when combined, will look just like this. So let's see if we can put it exactly in the form that we need. If I break this expression up across that subtraction, I will have this leading coefficient of 2n minus 1 times the integral from 0 to pi of just cosine, the cosine function raised to the 2n minus 2 dx, and then minus 2n minus 1 times 0 to pi of cosine x to the 2n minus 2 plus 2. So cosine of x raised to the 2n power. And you should have anticipated that because we expect to combine this with this, which we can now do. And when we do so, we're going to be bringing over 2n minus 1 copies and adding it to this, giving us a coefficient of 2n on the left-hand side. That doesn't really need parentheses, but yeah, let's just write 2n. Cosine x to the 2n power dx, leaving us with 2n minus 1 times the integral from 0 to pi of cosine raised to the 2n minus 2, which is like the even power that came before this one. And I wrote this 2n minus 1 kind of high because what I now plan to do is just divide by 2n like this. And that gives us exactly the form that we were looking for. So if n here is 1, then this is just pi, because it would be the integral from 0 to pi of 1 dx, giving us cosine squared is 1/2 pi. And that's what we already saw. You can now check, well, what if n is 2? Then we would have cosine to the 4th, the integral of that on the left, and that would be 3/4 times the integral of cosine squared. So you see we get our pattern that we were already able to write down from this general expression. Okay, I hope you enjoyed this computation. Thank you for your attention.